Hello, today we're going to look at the semi-empirical mass formula, or I could have called this the binding energy of the nucleus, or I could have called it what holds the nucleus together, or I could have called it why can't you have any number of protons and neutrons in a nucleus. So this is a subject based on nuclear physics, and if you haven't already done so, I advise you to watch my videos in the A-level playlist on the nuclear radius, nuclear physics and nuclear fission and fusion, because that will give a background to what we're now going to cover. This material is more than A-level. This is essentially university level physics. We know that an atom consists of a central nucleus, which is positively charged, with, and I'm talking classically here, orbiting electrons. We know that the nucleus itself consists of protons and neutrons. Protons are positively charged, so they contribute to the positive charge of the nucleus. Neutrons have no charge at all and don't contribute to the charge, but the net charge on the nucleus is positive. And there are an equal number of positive charges, that is protons, in the nucleus, as there are negative charges, electrons, orbiting the nucleus. Now, as we saw at A-level, if you make a plot of the number of neutrons versus the number of protons, the number of neutrons we put as n, the number of protons we use z. If you make a plot, I'm firstly just going to draw a line. That line is n equals z. That would be the number of neutrons equals the number of protons. But if you look at all the stable nuclei that there are, what you find is that at the low end, n does indeed equal z. But then the line diverts off toward the neutron end. And you find that stable nuclei with high values of z have more neutrons than they have protons. So there is an excess of neutrons in stable nuclei at the high end. In other words, when Z gets larger, the number of neutrons exceeds the number of protons. You also find that there are unstable nuclei surrounding this line, and I'll talk about what I mean by unstable in just a moment. So there are unstable nuclei both above and below this line. So stable nuclei represented by the crosses, unstable nuclei are represented by the circles, and if you like we could draw a dotted line around all of this. This is nothing more than a container. And that dotted line shows you all the nuclei that you can find naturally occurring. You don't find any here. You don't find any here, and you don't find any above this point here. And what we're going to ask in this video is why? Well, let's first consider what happens with these unstable nuclei. Now, as I've said, in the series of circles which are above the stable line, basically you've got excess neutrons, and below the stable line you've essentially got excess protons. And what happens with those unstable nuclei is that they will decay, they will change in order to get onto the stable line. So if you've got an excess of neutrons, what that means is that a neutron is going to decay into a proton. So you get a neutron becomes a proton plus an electron plus an anti-electron neutrino. If on the other hand you've got an excess of protons, then a proton will convert into a neutron. So proton converts into a neutron plus a positron plus an electron neutrino. We've seen those formulae before at A-level. And what is actually happening is that if you're here at this unstable nucleus here, what you're going to do is you've got too many neutrons. So if you convert a neutron to a proton, the neutron number will fall by 1, but the proton number will increase by 1. So what you'll essentially do, let me just draw it here, if that's your unstable position, that's this one here, you will fall down 1 on the neutron scale, but you'll increase 1 on the proton scale, so effectively you'll fall down in that direction onto a stable nucleus. So you'll become stable by decreasing the number of neutrons by 1, but increasing the number of protons by 1. Similarly, if you're on this position here where you're proton rich and you're going to change protons to neutrons, what you're going to do then, if you are at this position here, let's say, is you're going to decrease the number of protons by 1 and increase the number of neutrons by 1. So essentially your pattern, let's move this up a little bit like this, your pattern will be to decrease the number of protons by 1, increase the number of neutrons by 1, so you're moving diagonally in this direction onto the line of stability. So in both cases, you are changing either a neutron to a proton or a proton to a neutron, and what you do is you'll notice you emit either electrons or positrons. Now, before anybody knew what electrons were, this emission was given a name. It was called beta. In fact, people who were studying nuclei and their decay found that there were 3 types of emissions: alpha, beta, and gamma. Alpha was positively charged, beta was negatively charged, and gamma wasn't charged at all. That's how they knew that there was a difference. And these emissions are called beta decays. A beta particle is simply an electron. A beta plus particle is simply a positron. So this decay happens by what's called beta decay, which is simply, if you're changing a neutron to a proton, you emit an electron. If you're changing a proton to a neutron, you emit a positron. And this is the way that unstable nuclei get back onto the stable line. If you get to the very high end, you don't get electron emission anymore, you get alpha particle emission. Suddenly you've got to start reducing by significant numbers of neutrons and protons. An alpha particle is 2 protons and 2 neutrons, and if you've got an alpha particle decay, it means that an unstable nucleus will reduce its neutron number by 2 and its proton number by 2 and move on to a stable position in that way. Now, the question I'm essentially asking is, why is it that some nuclei are stable, some nuclei are unstable, and some nuclei don't seem to feature at all? What is causing this? And if we are speculating that there is a nuclear force, and we are, so we'll say here is the nucleus, and there's some kind of force that's holding it together. There must be, because there are protons and there are neutrons in this nucleus, and protons are positively charged, so there will be a Coulomb force, an electrostatic force between them, which will be a repulsive force, so it will be trying to push the protons apart and make the nucleus unstable. If the nucleus is stable, there must, as it were, be a stronger force, which we call the nuclear force, that's holding it together, and that force must be stronger than the Coulomb force that is trying to push it apart. Now, if there is this nuclear force, which is essentially putting its arms round the nucleus and saying, I'm going to hold you together, I'm going to bind you together, then what does it matter how many protons or neutrons you have in the nucleus if there's a nuclear force that's binding them? Well, if there is a nuclear force that's binding them together, then there must be some binding energy that is responsible for holding the nucleus together. And what is the source of that binding energy? Well, if you were, and this is just a kind of thought experiment, if you were to take a set of scales and take the total number of protons in a nucleus and the total number of, that should be N, the total number of neutrons in a nucleus, so we've got Z protons and N neutrons, but you just take the number of protons and the number of neutrons, just take each individual proton out of a box and the right number of neutrons out of a box and put them on these scales, and on the other scale you put the actual nucleus itself, which contains Z protons and N neutrons, what you find is that the mass of the individual protons and neutrons is greater than when those protons and neutrons are bound in a nucleus. There is what is called a mass deficit. Some of this mass has been lost when all these protons and neutrons are bound in the nucleus. And how does mass get converted into energy? Well, E equals mc squared. So what we're saying is that this very tiny amount of mass that is the deficit between the individual constituent particles and when they actually get bound together in a nucleus, that is responsible for the binding energy. In other words, the binding energy is the mass difference or the mass defect multiplied by c squared. Now, the mass of a proton is of the order of 10 to the minus 27 kilograms. And this mass difference will be much smaller than that. So we are talking tiny, tiny amounts of mass. But look, that tiny amount of mass is multiplied by c squared. C squared is 9 times 10 to the 16. So you're already, that's almost 10 to the 17th, you're already converting that, and that will be in joules. And if you want to convert joules to electron volts, not quite this, but you multiply by 10 to the 19. You actually divide by 1.6 times 10 to the minus 19, but we'll just look at orders of magnitude. So you can see that this is essentially 10 to the 17, this is 10 to the 19. All of this combined is a massive 10 to the 36 to get an energy in 10 to the 36 to get an energy in electron volts. So even though you've got a very, very small mass, smaller than the mass of a proton, you multiply that by 10 to the 36 to get EV. And what you actually find is the binding energy for a nucleus will not be in electron volts, but it will be in mega electron volts, MeV, as we shall see. Well, how are we going to measure this binding energy? Well, on the face of it, it's pretty straightforward, because we know that we've just got to find the mass deficit and multiply it by c squared. Well, to find the mass deficit, what we need to do is to multiply the mass of a proton by the number of protons, plus the mass of a neutron, which we know, times the number of neutrons, and subtract from it the nuclear mass of the atom. Trouble is, measuring nuclear masses is more difficult than you may think, whereas measuring atomic masses is very easy. John Dalton, for example, the chemist, was measuring atomic masses way back in 1803, long before, 100 years before anybody even knew what a nucleus consisted of. John Dalton was measuring atomic masses. So the real question is, can we find a way of measuring binding energy of a nucleus from atomic masses and the knowledge of the mass of a proton and the mass of a neutron, which we can measure? So let's consider an atom, which I will give the symbol X. It doesn't stand for anything, it's just any atom which has Z protons and A nucleons. Nucleons means protons plus neutrons, so essentially A is equal to protons plus neutrons. So if you want to know how many neutrons are, they are obviously A minus Z neutrons. So what is going to be the constituent bits of this atom? Well, there are going to be Z protons, so we multiply Z times the mass of a proton gives us the total mass of protons, plus N times the mass of a neutron gives us the total mass of neutrons. And then, of course, there'll be electrons, and there are always the same number of electrons as there are protons, so there'll be Z electrons. So we multiply the mass of the electron by Z, and that gives us the total mass. And to convert that to energy, we have to multiply by c squared. So all of that is a mass multiplied by c squared gives you an energy. And that is going to be equal to the atomic mass, so I'll put M at, atomic mass, of this element here, X, Za plus the binding energy of the nucleus plus, if I can get it in, the binding energy of the atom. Because remember, not only is the nucleus bound, but the atom is bound. A hydrogen atom, for example, the binding energy of a hydrogen atom at its lowest level is minus 13.6 electron volts. In other words, you have to provide, if you've got a hydrogen atom, the electron is bound to that atom, and if you want to get that atom to escape, you have to provide it with more than 13.6 electron volts in order to give it enough energy to escape. This is, of course, nothing more than the photoelectric effect. Here is the hydrogen atom. It's got one proton. It's got one orbiting electron. The positive and the minus charges are attracting, and that means that the electron is bound to the atom, and it is bound by 13.6 electron volts. You have to provide that to get it out. The photoelectric effect doesn't use hydrogen, it uses a metal, and what it says is if you shine light, it usually has to be ultraviolet light, on the metal, you provide energy, and that will cause the electrons to come off. And what is the energy of ultraviolet light? It's Planck's constant times the frequency of the light. So, in other words, the higher the frequency you need, the higher the energy you need, the higher the frequency of the light you have to use. And for hydrogen, for example, 13.6 eV, which is what this energy would have to be, turns out to be a frequency in the ultraviolet range, which is why you'd have to use ultraviolet light. And the same applies to metals. Although the binding energy for metals will be slightly different, nonetheless, you still need ultraviolet light to give enough energy to kick the electron out, because the electron is bound. So we've got two terms for binding energy: the binding energy of the nucleus, which is actually much larger because that will be in MeV, and the binding energy of the atom. So I'm just going to slightly rewrite this formula here, and I'm going to write that as Z into MP plus Me, because we've got Z protons and Z electrons, times C squared, that's an energy term, plus you'll remember the mass of the neutron multiplied by the number of neutrons, C squared, is equal to the atomic mass of the atom, AZX, plus the binding energy, nucleus, plus the binding energy, atomic. Now, the reason I rewrote that, let's just show you the old formula. All I've done is to take these two terms out, and then that term is left. So essentially I've just rewritten it like that. The reason I've done that is that if you take this term here, that is, I'll rewrite it, MP plus MEC squared, is not that the energy of the mass of a hydrogen atom? So that is the constituent bits of a hydrogen. So I'm adding the two masses together multiplied by C squared to get an energy, and that is going to be the atomic mass of hydrogen multiplied, of course, by C squared, plus the binding energy of the hydrogen atom, because the hydrogen atom is bound. So in other words, we're saying that there's a very tiny mass difference between the individual constituent elements of the atom and when the atom is bound. And the difference between the two, the mass difference, is what provides the atomic binding energy. So if I take this formula here, I can say Z. Now instead of MP plus MEC squared, I can now write this term here. So I'm going to put Z times the mass of atomic hydrogen times C squared plus Z times the binding energy, that's this term here, of a hydrogen atom. That's that now rewritten in a different way. Then I've got to add my n c squared, the number of neutrons times the mass of a neutron times c squared, is equal to what we had before, the mass of the atomic AX plus the binding energy of the nucleus plus the binding energy of the atom. Right, now where can we go from there? I want to know what the binding energy of the nucleus is. That's what we're trying to find here. And so if I rearrange this formula, I will get that the binding energy of the nucleus is equal to... well, before we do that, let's just think for a moment. Here we've got Z times the binding energy of the hydrogen atom. And here we've got the binding energy of this atom X with Z protons. The binding energies of atoms are in eV, electron volts, whereas the binding energy of the nucleus is millions of times bigger in mega electron volts. When you bring this term over to this side, because you want binding energy alone on this side, you're going to get Z times the binding energy of a hydrogen atom minus the binding energy of this atomic atom X. The difference of two very small binding energies is going to be very, very small. Consequently, those two terms really are irrelevant. They are so close that when it comes to a binding energy of the order of MeV, they're really not going to matter. So now we can rewrite our formula with binding energy is equal to Z times the atomic mass of hydrogen times c squared plus nmnc squared, so the number of neutrons times the mass of a neutron times c squared, minus this term here, the atomic mass of the element X with Z protons and A nucleons. And that's it. Now, even John Dalton could measure the atomic mass of X. We know, and indeed he measured the atomic mass of hydrogen, and we know the mass of a neutron. So we know these atomic masses, we know the mass of a neutron, we know the number of protons, and we know the number of neutrons, so we can calculate the binding energy of the nucleus. And all of this comes from experimental data. So, for example, we showed you that the binding energy of a hydrogen atom was 13.6 electron volts. The binding energy of a helium nucleus, for example, is 28.3 MeV. It just shows hugely greater than the binding energy of an atom. And what this means is that by measuring the atomic, you only need to measure the atomic mass of hydrogen and the atomic, or the mass of a neutron once, and you've got those two terms forever. You've just got to measure the atomic mass of all the elements, and for each element, using this formula, you can calculate the associated binding energy of the nucleus. So the nuclear binding energy can be calculated from experimental results for all nuclei. So the binding energy is, as it were, the energy that is holding the nucleus together. And the nucleus consists of protons and neutrons. And we know that were there to be no binding energy, the protons would force the nucleus to disintegrate because they would repel and push the nucleons apart. And the binding energy overcomes this and holds them together. But now let's ask, what is the actual source of the nuclear force that is providing this clinging, this, as it were, cementing of the nucleons together? Well, let's postulate for a moment that the force is actually simply a force that acts between any two nucleons. So whether it be a proton and another proton, proton and a neutron, or a neutron and a neutron, we're going to speculate that there's a force that acts between them that holds them together. So in other words, the more pairs of nucleons you have, the stronger will be the force, because each pair is contributing one bit of the force. Well, how many pairs do you get? Well, let's think about the number of nucleons. If you've got, say, 3, 1, 2, 3, how many pairs are there? There are 1, 2, 3 pairs. If you've got 4 nucleons, 1, 2, 3, 4, then you've got 1, 2, 3, 4, 5, 6 pairs. And for A nucleons, and this is just purely mathematical, you can show that that is equal to A into A minus 1 divided by 2 pairs, which is of course equal to A squared minus A divided by 2 pairs. I mean, work it out. When A is 3, that would be 3 times 2 is 6 divided by 2 is 3 pairs. When A is 4, that's 4 times 3 is 12 divided by 2 is 6 pairs, so it seems to work. So the total number of pairs when you've got A nucleons, which is total number of protons and neutrons, is A squared minus A over 2. So this means we're saying that since each pair is contributing towards the nuclear force, the total force, or if you like the total binding energy, is going to be proportional to the number of pairs, which is A squared minus A over 2. So very roughly you can say that the binding energy, the total binding energy of the nucleus, is proportional to A squared. Particularly as A gets larger, this A term is of less significance. Very roughly, the binding energy of the nucleus is proportional to A squared. Makes sense. As A increases, you'd expect the binding energy to increase. So if I divide both sides by A, I get that the binding energy of the nucleus divided by A is proportional to A itself, which would mean if I drew a graph of binding energy over A, the total number of nucleons, against the number of nucleons, I would expect that to be a straight line. Don't know what the gradient would be, but it would be a straight line. Now in practice we know how to measure the binding energy. I've just shown you, you do it from atomic masses, and you can deduce the binding energy, the nuclear binding energy, for all elements. And what you find is if you actually plot the experimentally determined binding energies per nucleon against A, that what you actually get is something that looks like this. There's a very steep rise initially, but then it peaks and there's a very slow fall off. And it peaks at A equals iron 56. That is where you get the maximum binding energy per nucleon, and that is roughly 8 MeV. So 8 MeV per nucleon, there are 56 nucleons, so there will be 56 times 8 MeV total nuclear binding energy. And there's a very slight fall off, but it's almost a constant. And right at the beginning of the periodic table, the hydrogens and the heliums, they are much less bound. The binding energy per nucleon is much smaller, as we'll see in a future video. So very roughly you could say that the binding energy per nucleon is equal to 8 MeV, because that's roughly what the position is at this stage of the business. And that means that BE is proportional to A and not A squared, as we speculated up here. So we've obviously made a mistake if the binding energy is only proportional to A rather than A squared. So where have we gone wrong? Well, our problem probably is in the assumption that the binding energy is caused by all nucleon pairs. Here's a nucleus, here's a nucleon, and here's another nucleon. And we were speculating that no matter where the nucleons are, they all exert a nuclear force between them. And the total number of nuclear forces is the total amount of pairs multiplied by the nucleon force for each pair of nucleons. But this, in a large nucleus, this might be 5 Fermis across. Suppose the nuclear force doesn't have that range. In fact, we do know that nuclear force is very short range. Suppose two nucleons on either side of a nucleus actually don't have any interaction because in a sense they're too far apart. Let's suppose that actually this is a very short range force, so that actually the nucleons can only interact with the nucleons immediately around them. So they each have an interaction panel, but this one doesn't interact with this one. So we're no longer saying that the binding energy is proportional to the total number of pairs. We're essentially saying that the binding energy per nucleon is a constant because for each nucleon it's only the immediate nucleons around it that are contributing to the binding energy for that nucleon. Now the total binding energy will obviously therefore be proportional to the atomic number A, but not A squared, because as the atomic number grows, so you're going to have more nucleons, and each nucleon will have its own little cluster, and that little cluster is providing the binding energy. So now you can say that the binding energy is proportional to A. The binding energy per nucleon, of course if you say B divided by A, is proportional to a constant, so it is actually a straight line. And that is because it doesn't matter how many nucleons there are, each nucleon only sees, as it were, or only interacts with the ones in its immediate vicinity. So we can now say that the binding energy, the total binding energy of the nucleus is proportional to A, and that means let's call it is equal to a constant, which I'm going to call AV, standing for volume, times A. In other words, the binding energy of the nucleus will increase as the number of nucleons increases, but not as the square. But I'm afraid we're going to have to make some corrections to this. You see, the first thing we've got is we've forgotten that there is a surface to the nucleus. Again, I'm talking in classical terms. In quantum mechanical terms, that surface would be very fuzzy, but that nucleon there is different from this nucleon here. This nucleon has got nucleons all around it in its interaction mode. But this one has got these, but the one that would be there isn't there because it's at the surface. So the total binding energy for that nucleon is slightly less than the nucleons that are in the middle because there's not so many local pairs. So the binding energy is reduced because of this surface effect. So I've got to put a minus here because I'm reducing the binding energy as a consequence of the surface. What is the surface? Well, it's 4 pi r squared, where r is the radius. And we learnt in our A-level physics that the radius is equal to some constant, which we call r0, times a to the third, where a again is the nucleon number. So obviously r squared is going to be proportional to a to the 2/3. You just square both sides. Consequently, we can say that the correction term that we need to put into this is going to be proportional to a to the 2/3. And what we actually say is there's a constant of proportionality, which we'll call the surface term, that's a constant, times a to the 2/3. And that term is reducing the binding energy because the nucleons on the surface aren't experiencing quite as much binding energy as those in the middle. So that's why it's a minus term. It reduces the amount of binding energy. But there's another correction term that we need. Here's the nucleus. It's made up of protons and neutrons. The neutrons don't have any Coulomb force, but the protons certainly do. They are trying to push one another apart and break up the nucleus. So they are essentially acting in the opposite direction of the binding energy. The binding energy is trying to keep them in, the Coulomb force is trying to push them out. So we need another minus term here because we've got a Coulomb force that is reducing the binding energy. What is the nature of that force? Well, we know that the force is equal to Q1, Q2, the charges on the two protons, divided by 4 pi epsilon naught r squared. That's the force. We're talking about energy. The potential energy is given as Q1, Q2 over 4 pi epsilon naught R. So it's just a 1 over R dependence, which of course is just a constant because these are going to be the charges on the protons, which is constant. 4 pi epsilon naught is a constant. So the only variable here is R. And as we've seen, R is proportional to A to the 1/3. So we just need to put A to the 1/3 here. That is going to be the potential energy between any two protons. How many pairs of protons are there going to be? Well, just as before, the total number of pairs, if there are Z protons, the total number of pairs is Z into Z minus 1 over 2. So as it were, the potential energy term that we're going to need to put in will have a Z into Z minus 1 divided by A to the 3rd. The 2 we can wrap up in this constant. So we now need to have because this is the total number of proton pairs, this is the contribution to reducing the binding energy of each pair. So you multiply this by this and you take the 2 and you wrap it up in the constant. So now we need this minus term here, which is Z into Z minus 1 times a constant, which we'll call AC, that's the Coulomb constant, divided by A to the 1/3. And that is the classical bit done. But there are 2 more, as it were, quantum mechanical corrections to be made. The first recognises the Pauli exclusion principle, that you cannot have all these nucleons at the same energy level. They are going to occupy energy levels. The way it works is that 1 proton spin up and 1 proton spin down, and 1 neutron spin up and 1 neutron spin down can occupy the lowest level, but then that level is full. So further protons have to occupy spin up, spin down, and neutrons spin up, spin down, the next energy level, and so on, until you've used up all your protons. And let's say that we use up all our protons when we get to this level here. But for, as we showed, there is an excess of neutrons over protons when you get to higher values of A. So now you've got to accommodate the excess neutrons. And they are going to build up, spin up, spin down, spin up, spin down, and so on, until all the neutrons have been accommodated in the energy levels. But that, you will see, produces an asymmetry. You know, there's a low level energy here, there's a higher level energy here. These neutrons up here are at a, as it were, lesser binding energy. It's easier to kick one of those neutrons out than it is one of these protons, because this is binding energy, goes down in this way. Energy equals 0 is here. Consequently, this is nearer to 0 than this is, and you need less energy to kick this out than you do to kick this one out. It's rather similar to, the electron in the atom. This is minus 13.6 eV for a hydrogen atom, but if that electron is at a higher energy level, where this of course is E equals 0, then you don't need 13.6 eV to kick that electron out, you need much less. Well, what we want to know is, what is the extra energy associated with these kind of excess neutrons? Let's assume that the energy difference is delta for each energy level. Then what you're going to have is an energy excess caused by these neutrons, which is going to be 2 neutrons which are delta higher, so that's 2 times delta, plus another 2 neutrons which are now 2 delta higher because they're 2 levels above, so that's 2 into 2 delta. And then if there were more, it would be 2 into 3 delta, because you'd have 2 more neutrons that were 3 delta higher than the proton level, all the way up to 2 into x over 2 delta, where x is the number of neutrons in excess of the number of protons. So x is the number of excess, as it were, neutrons over protons, and it's x over 2 because you will only have half the number of energy levels, because each energy level can accommodate 2 neutrons. Now this is a geometric series, and you can simply reduce it to E. That's the excess energy of the neutrons, because they're in this asymmetric arrangement, is equal to 2 delta into x over 2 into x over 2 plus 1 divided by 2. That's the geometric series. Those two 2's cancel out. So you've now got delta into x squared over 4, which is those two terms, plus x over 2. So I've rewritten that formula that as it were, the energy excess consequence of having these asymmetric neutrons is delta into x squared over 4 plus x over 2. Now, what is the size of delta? Well, what we're arguing is that delta is the separation between the energy levels. And generally speaking, the greater A is, the less delta will be. So as A increases, the energy levels are squeezed together. That means that delta is proportional to 1 over A. So I've got, for my delta term, I can replace that by a 1 over A term. What is x? Well, x, remember, was just the surplus of neutrons over protons. It's n minus z. X will be small compared to x squared when we've got larger numbers. So again, we can ignore the x term, and essentially we can wrap up all the constants into a single constant. The only things we've got are a delta, which is a 1 over a term, and an x squared, which is an n minus z squared term. So essentially the correction term we're going to need here is a constant, which we'll call the symmetric constant, times n minus z all squared, which is essentially this x squared term, divided by a, which is essentially the delta term. And now I'll rewrite our binding energy formula, starting over here. So the binding energy of the nucleus is equal to this volume constant times the total number of nucleons. And then we have to subtract from that the surface term. Then we have to subtract from that the Coulomb term, z into z minus 1 over a to the 1/3. And now we have to minus this symmetric term, a symmetry n minus z all squared. Yes, I've just got that in brilliantly, over a. Now there is one final term that we need to consider, and that is what's called the pairing term. Because it turns out that if you've got 2 protons, they form a pair and their binding energy is much greater than if you've got an isolated proton. Similarly for neutrons. So if you've got an even number of protons and an even number of neutrons, they can all form pairs and you get a high binding energy. If you've got an odd number of protons and an odd number of neutrons, then when they form pairs, there's always going to be one poor old proton and one poor old neutron left over without a partner. That actually reduces the binding energy because those isolated proton and neutron are easier to get out of the nucleus. They're not bound by this pair, so their binding energy goes down. And basically, if you've got an even and an odd, so an even number of protons, odd number of neutrons, or t'other way round, kind of evens out. So what we've got to do with this binding energy term here is to add just one more term to it, which I'm going to put down here. I'm just going to call it delta. It wasn't the delta we used before. This is now the representing the proton pair issue. And that delta is going to be, since it contributes, a plus term. So if it's positive, it will increase the binding energy. So even will be positive because that increases the binding energy. Odd will be negative because that decreases the binding energy. And odd even or even odd will be 0. Okay, so when we come to delta, we'll have either a plus term for even, a minus term for odd, or 0 if it's odd even or even odd. So now we can go back to the basic equation we came up with right at the beginning, where we said that the nuclear mass of an atom, which is Za, so the nuclear mass of this particular atom X, times c squared, because that converts it into energy, is equal to the mass of the individual components. So it's Z times the mass of a proton, c squared, plus n times the mass of a neutron, c squared. That's the individual masses of all the protons plus the individual masses of all the neutrons, minus the binding energy. Because when you form a nucleus, you lose some of this mass. Some of this mass is taken away and is converted into energy called the binding energy. But we've just calculated, and that's the nuclear binding energy, of course. We've just calculated that nuclear binding energy. It's this great long formula here. So if we were to put that term into here, we end up with the semi-empirical mass formula. And there it is. Let's go through it again. The nuclear mass of any atom, but we're just looking at the nuclear mass, not the electrons, times c squared to convert it to energy, is equal to the total number of protons times the mass of each proton times c squared, so that gives you the proton energy. The total number of neutrons multiplied by the mass of each neutron gives you the total neutron energy, minus the binding energy, which is the volume term, the surface term, the Coulomb term, the symmetric term, and the pairing term. And that is known as the semi-empirical mass formula. Empirical means that you fit things with experimental results, but you don't have very much by the way of theory behind it. Semi-empirical means you fit with experimental results, but you've got a loosely based theory. You know, this was all fairly hand-waving, but it's at least based on some kind of theory. Well, what that means is that we ought now to be able to calculate the mass energy of the nucleus of any atom. But before we do that, let's just have a look and see how that binding energy formula affects the graph. Binding energy per nucleon divided by, plotted against the nucleon number. If you take just the first term, binding energy equals a constant times A, that means that the binding energy per nucleon is a constant. You would just get a straight line. If you take the first two terms, binding energy is AV times A minus the surface term, but you divide per nucleon, what you start to get is something that looks like that. So the binding energy is still increasing with nucleon number, but it's now slightly different from just being a straight constant. If you now add this Coulomb term, then what you get is something that looks a bit like this. And if you add the symmetric term, you get a slightly declining line. And that is not dissimilar from the experimental results with iron 56 at the maximum. And a very slightly tailing away line here. And this is all at about 8 MeV, which is precisely what experimentally you observe. So by putting in those first four terms, I haven't bothered with the pairing term, but certainly by putting in those four terms, you get a binding energy per nucleon which accords pretty much with the experimental results that I showed you earlier. Well, this is all very well, but we haven't found the values of the constants AV, AS, AC, Asim and delta. Well, I told you earlier that we can now measure the binding energy of the nucleus by knowing the atomic mass of hydrogen, the mass of a neutron, and the atomic mass of each element. So as long as you measure those things experimentally, you can calculate the binding energy of all the nuclei. So for all nuclei, and there are, after all, there are 92 atoms, but you can have more than one nucleus. You can have a stable, you can have unstable nuclei. For all of those, you can calculate the binding energy. You know for each of those atoms what the A number is, you know what the Z number is, you know what the N number is. So essentially you can create 92 equations if you wanted to, one for each element, with in each case A, Z and N would be known, and you can find the nuclear energy, and so you get 92 of these equations, of which everything is known apart from these 5 constants. Well, 92 equations and 5 constants, 5 unknowns, pretty easy. You can just get the constants falling out. Problem is that those constants vary depending on precisely how you do this. So I'm just going to quote you one set of constants. If you are being taught a different set, that simply means a slightly different experimental method or a slightly different actual calculation method. But the values are not quite so important as knowing roughly what they look like. And what you find is they're all, of course, measures in energy. AV, the volume term, from my point of view, is 15.8 MeV. AS, the surface term, I should put equals there, is 18.3 MeV. The Coulomb term, very much smaller, 0.714 MeV. The symmetric term is 23.2 MeV. And then delta, which you'll remember was the pairing term, well, that turns out to be 33.5 MeV if you're talking even. It's minus 33.5 MeV, as we said, odd, because that is actually acting against the binding energy, and it's 0 if it's odd even or even odd. So now we know it all. We've got a formula for the binding energy. We know the values of the constants. So for you give me any atomic nucleus you like with values of A, Z and N, and I can calculate from that the binding energy of the nucleus. So the question remains, why then can you not have a nucleus with any old number of protons and nucleons and have stability? After all, the nuclear forces are holding all these things together. You should be able to have any number of nucleons and any number of protons you like, put those in that formula and derive a binding energy. What's the problem? Why can't we do that? Why are some nuclei unstable? And why don't some nuclei exist at all? And the answer is very simple. It is nature's insistence that it always wants to occupy the lowest energy. That's essentially all there is to it. So here is our semi-empirical mass formula, which we derived earlier. And yes, in theory, you could put any number of Z's and any number of N's, and don't forget A is constrained, A is Z plus N, but any old Z's, any old N's into this formula, and you would generate the nuclear mass of the associated atom. But nature says, when you give me a certain number of nucleons, I want to occupy the lowest possible mass energy. That's the one that will be stable. In other words, for any given value of A, and I'll just remove the semi-empirical mass formula for a moment, we'll put it back. But let's say, for example, that we fix A equals 100. how many combinations of Z and N can we have? Well, Z plus N must equal 100. But we could have everything from Z equals 100 and N equals 0 to Z equals 0 and N equals 100. That's 101 combinations of N and Z, all of which add up to 100 because I have fixed A at 100. So let's bring back the semi-empirical mass formula. So I could fit all the different values. A would be 100 in each case, but I could put Z and N with all the values such that Z and N always equal to 100, but you start with Z is 100, N equals 0, then you do Z is 99, N equals 1, and you calculate the mass energy for all those atomic nuclei. And what nature says is, I want to occupy the lowest energy that you calculate. So for all the possible values of Z, what is the value of Z that will give us the minimum value of mass energy? To find a minimum, you differentiate and set equal to 0. So we differentiate the mass energy by Z, which is going to be our variable, and set that equal to 0. So take a deep breath and let's do it. Follow closely. So hang on to your hat, here we go. We're going to take the differential of the mass with respect to Z. And then we're going to set that equal to 0. So let's do it. Our first term is ZMPc squared. Differentiate that with respect to Z, you just get MPc squared. Here we've got NMNc squared. Well, N is Z dependent because N is simply A minus Z. So if you replace N by A minus Z, you get AMNc squared, which of course is not Z dependent, so that will go. But then you'll get minus ZMNc squared, and when you differentiate that with respect to Z, you're going to get minus MNc squared. And what we've got here before we move on is the difference between the proton mass energy and the neutron mass energy. That is less than 1 MeV. For these purposes we can ignore it. The difference between the two is fairly trivial in these terms, so we'll ignore that. That took care of that particular term. Now we come to the binding energy. We start with minus AV times A. That is not Z dependent because A is fixed, remember, so that gives us nothing. The second term is minus times a minus, which is plus AS, A to the 2/3, again not Z dependent, so that gives us nothing. Now we've got a Z dependency here. We'll start with minus, well it's minus times a minus, so it's plus AC over A to the 1/3, AC over 1 to the A to the 1/3, and then we've got a Z squared minus Z. Z squared minus Z differentiated with respect to Z gives you 2Z minus 1, right? That's differentiating Z squared minus Z with respect to Z. And then we're going to get a minus times a minus, which is a plus, this asymmetric term. Now, N is A minus Z, and therefore N minus Z is A minus 2Z. I'll just write that down here, A minus 2Z. That is N minus Z because N is A minus Z. But this is squared, and that's going to give us A squared minus 4AZ plus 4Z squared. That is the square of this. And now we need to differentiate that term with respect to Z. The A squared term will go, and that's going to give us minus 4A plus, differentiate 4Z squared, you get 8Z. So that was all by way of calculation. So I'll just put a ring around that to show that that was just a kind of a calculation. So we now know that the symmetric term is going to be, and I'll push this up here, so this comes down here to become the symmetric term, which is plus A sim over A, which is this term here multiplied by the differential here, which we just calculated as minus 4a plus 8z. And then finally we've got delta. Delta is not z dependent, so that's going to give us another 0 when we differentiate. So when you look, we've now got differential of mass with respect to z is equal to nothing, nothing. We've got a Coulomb term and we've got a symmetric term, and that's it. So now what we do is to set that equal to 0. And what I'm effectively going to do is to jump, well here, let's set that equal to 0, there you are, set it equal to 0. Now I'm going to rewrite that equation, bringing the z's on one side and the just pure non-z constants on the other side. So from this term here I've got a z into 2ac over 1 to the third. So I've got z into 2ac divided by a to the 1/3. That's that z term there. And the z term here is 8 asim over a. So 8 asim over a, that's plus 8 asim over a. Those are the only two z terms, that z term there and this z term here. On the other side, I'm going to have, well, minus ac over a to 1/3, but put it over the other side becomes plus ac over a to the 1/3. And then down here I've got a minus 4a asim over a, so the a's are going to cancel. I've got a minus 4 asim, take it over the other side, it becomes a plus 4 asim. And that means that I can write that z is equal to this term here, ac over a to the 1/3 plus 4 asim, divided by this term here, 2ac over a to the 1/3 plus 8 asim over a. Now if we observe this formula, what we say is we know all of these terms. A was fixed. You can choose any value of a you like, but having done so, it's fixed. In my example, I chose 100. We've already established what the constants are. So if you plug this in, you will get a value of z, which will be the preferred value of z. That will be the value of z that gives you the stable nucleus. If you did simplify this further, you would find that this reduces to z equals a over 2. As I say, there's no need to do it because you can just fill in the necessary values here in a spreadsheet and it calculates it for you. But if you insist on going further, you will get very roughly that z is equal to a over 2 into 1 over 1 plus 0.008 a to the 2/3. And if we examine that, what you'll find is that when a is very small, this term is very small, and therefore this whole term is 1. So z is a over 2. In other words, if you've got a small number of nucleons, a, half of them will be protons, and of course the other half will be neutrons. And that's exactly what you find. If you look at carbon 12, that has 6 protons. Nitrogen 14 has 7 protons. Oxygen 16 has 8 protons. In each case, it has half the number of protons of the overall nucleons. But as A gets larger, this term will increase, and consequently this fraction will be less than 1. If it becomes less than 1, that means that Z will be less than A over 2. Less than half of the nucleons in a stable atom where A is larger will be protons and the remainder will be neutrons. So that explains why there are more neutrons than protons when you get to the higher values of A. Now if we look at my now corrected semi-empirical mass formula, you will observe that the mass of the nucleus is a function of, well, what is the actual terms? In some cases you've got constants, where there is no Z dependence at all. In some cases you've got single values of Z, and in some cases you're going to get Z squareds. You're going to get Z squareds from here, you're going to get Z squareds from here. In other words, you can say that the mass, the nuclear mass, is going to be equal to a formula which looks something like A plus BZ plus CZ squared. Right, you could rearrange this formula so all the constants were brought together as A, all the values of Z on its own were brought together with a constant B in front, and all the values of Z squared were brought together with the value C in front. That is a quadratic equation in Z, and it is of course a parabola. What that means is that if you plot the parabola, here I'm going to plot the mass energy against different values of Z, and what am I going to find? I'm going to find a parabola that looks like this. Now, if this is an odd A, that is to say the nucleon number is odd, 117, 79, not even, what you're going to find is that for all the values of Z, you're going to get different energies, and those energies will fall on a parabola. And what nature says is, I want to occupy the lowest level. So, for any given A, which in this case is odd, this is the one, this value of Z is the one that's going to give you that stable nucleus. What happens if you create this one with a lower value of Z? Well, then that will decay by dropping in energy terms to the lower energy one. How does it do that? It has to increase the proton number by 1, so it has to convert a neutron into a proton, and that means you get electron or beta minus emission. If you create this nucleus, nature says, I can go down a bit to a lower level by reducing the number of protons. That means a proton gets converted to a neutron. That means you get positron emission or beta plus emission. So this way down the scale you're getting beta minus emission. This way down you're getting beta plus emission. And nature insists that she will only be satisfied when she's at the stable level, which is when Z is equal to this value for any given value of A. And that of course means that although you can have any theoretical value for Z, only one of them will be stable. And only one or two on either side will be unstable. What you will find is once you get too far away from this equilibrium position, some of these nuclei won't even exist at all, and we'll find out why in a moment. Now, I said that this was for an odd number of nuclei, which means it's an odd-even or an even-odd arrangement, and in that circumstance you remember the pairing constant equals 0. What happens if we've got an even number of nucleons? So we're now going to do an even value of A. If we look at this quadratic term up here, the delta term that features in the semi-empirical mass formula is not Z dependent, so that sits here. So for an even-even arrangement, A will be higher than for an odd-odd arrangement. And what that does to the parabola is it simply says there will be two parabola, depending on whether for this even number of nucleons, you can have an even number if you have even plus even or odd plus odd. Both will give you an overall number. But what you find is that the even parabola is lower than the odd parabola because it's the value of A in the quadratic equation which changes, and all that does is to push the parabola up or down. It doesn't change its shape, so I should have drawn two equal shapes. And what you will find is that this is a value of Z on the odd parabola, but you may get this and this on the even parabola, and then you'll get another value here and another value here on the odd. Right, what happens when the nucleus gets to this value of Z? Is that the end of the story? Not a bit of it, because nature says I can either go here or I can go here, either by beta minus or beta plus emission, in order to get to lower energy levels. And consequently, these two nuclei will be stable. Now you might say, oh, but what happens if one of them is a slightly greater energy level than this one? And it doesn't look it on my chart, but it could be. Does that mean that this would decay to this? Well, the answer is there is a theoretical possibility that it could. But look, in order to do that, it has to jump not one proton, but two protons, because these are 2 protons apart. And that would require a double beta decay. And whilst that's not impossible, it's significantly unlikely. So what nature does is it settles and it says, okay, both of those can be stable. And that's how you can find two nuclei with the same even A number that have stability. Now you can also have almost the same arrangement. This, incidentally, just to remind you, is the mass energy versus Z. And once again, we're having an even A. So we can have even plus even neutrons plus protons, or odd plus odd neutrons plus protons. And once again, we get the same parabola. This is the even parabola. This is the odd parabola. They're both exactly the same. They're just displaced because of that delta function, which was the pairing function in the semi-empirical mass formula. And now you might have a Z value here on the even parabola. Now that clearly is going to be the very lowest energy you can possibly get, so that's definitely stable. Then you might get your next values of Z would be here. So you get two elements there. And then you might get other elements here. Now this one is definitely stable because this is certainly at the lowest energy level. But what happens if you've got this one here? This can decay in two ways. It can either decay down to that one, which is the most stable of all, but it can decay to that one. And similarly, this here can decay to the most stable of all, or it can decay to that one. In both cases, you're reducing the energy, which nature likes. But suppose you do decay to this one. Will nature then say this one must decay to this one? Well, no, because we're now 2 protons apart again, and again you'd need double beta emissions, and whilst not impossible, it's unlikely. So now nature says, on this occasion, there can be 3 stable nuclei, because in order to get to single one, I'd have to have a lot of double beta emissions. So you can see that when you have an odd number of nucleons, there's usually only one possible stable nucleus. When you have an even number of nucleons, you might have 2 stable nuclei, or in some cases, you might have 3 stable nuclei. But all the rest will be unstable because by decaying, they can get to lower mass energy levels. So let's go back to where we started, which was the neutron-proton chart, where we said this was essentially the neutron equals proton line, but now we know why for stable nuclei, neutrons equals protons at the early stage, but we now know why there are more neutrons than protons as the nucleon number increases. We also know now why there are unstable nuclei on either side, because they are the ones that are further up the parabola in terms of energy, and therefore they are going to decay until they get to the lowest mass energy. So we know that, but the question we want to ask ourselves is, why is it all constrained in that single element, in that single box, if you like? Why is there nothing here? Why is there nothing here? And why is there nothing up here? Well, let's take this region here first. So let's fix a Z value, okay? And let's find the stable nucleus for that value of X. Sorry, that value of Z. If you put more neutrons in, you get to a neutron-rich environment in which the neutron will decay to a proton in order to get back onto the line of stability. That we know. But suppose you try and put so many neutrons in that you end up here. Then a new form of decay becomes favourable energetically, right? Nature says I want to operate at the lowest mass level, and what happens is you don't just get beta decay, you get neutron emission. You've got too many neutrons, it becomes energetically favourable for the neutron just to come out. And so what happens is you've got this element that you think you've created with XZA, let me push that up, XZA, but that is sitting up here, so there's a very high number of neutrons, and what happens is that one of those neutrons will be kicked out. The protons aren't changed, so it's the same element, it still has the same number of protons, but one of the neutrons goes, so the A number drops by 1, and you get a whole neutron emitted. And why will that happen? Very simple. The mass energy of this must be greater than the mass energy of this. So the mass energy on this side is M1, the total mass energy on that side is M2. If M1 is greater than M2, then neutron emission will occur in this case. And what you find is that the line that separates the position where you can have unstable nuclei, but at least they exist and can decay into stable nuclei, and the position where the nuclei can't exist because they will immediately emit a neutron and fall backwards. You know, if you emit neutrons, you fall back down this line into the safety zone, as it were. Anything in this region, you're going to get neutron emission. And the line that separates them is called the neutron drip line. What about the other way? Why can't we have a nucleus here? Well, once again, if we take a fixed Z, there's the stable value for the number of neutrons. Or if you like, we can go that way, that would be stable. We've got far too many protons. So now we can get what's called proton emission. So we start with our element. I'll take the same element. And that will decay to, and now we're going to decay by a proton. So if you lose a proton, you're going to change the element. X will now change to Y because Z will be Z minus 1. And A will be A minus 1 because a proton has gone, so that affects both numbers, plus a proton. And why will that happen? Because the mass energy on that side is greater than the mass energy on that side. And if that's the case, the proton is spontaneously emitted, and so you won't ever get anything here because the proton just is chucked out of the nucleus because it's energetically favourable to do so. And the line that separates the position where you have unstable nuclei, too many protons, but nonetheless they will decay, to the position where the nucleus just can't keep hold of the proton, that is called the proton drip line. And finally, as you might say, why then is there nothing up here? Why can't the stable nuclei continue to grow with increasing values of N and Z? What you will tend to find is that when Z is about 110 and when n is about 160, roughly, you won't be able to go beyond that. And the reason for that is that now alpha decay is happening. And alpha decay is the spontaneous emission of an alpha particle, which is 2 protons and 2 neutrons. So now you're going to have the element which would be up here with Z protons and N neutrons. But what it will do is quickly decay into a new element, because the number of protons goes down by 2, the number of nucleons goes down by 4, because you lose 2 protons and 2 neutrons, and you get a alpha particle, which of course is just a helium nucleus being emitted. Or energetically you may even find that and I'll just draw it, the heavy nucleus, because this is a nucleus with over 100 protons, over 150 neutrons. This heavy nucleus, instead of just emitting an alpha particle and becoming a slightly smaller nucleus, could well fission, which means it becomes 2 much smaller nuclei, and then very often plus an alpha particle as well. And why will either this or this happen? It is because the mass energy of the left-hand side is greater than the mass energy of the right-hand side. Nature's desire to get to the lowest energy level means that if your starting mass energy is greater than your finishing mass energy, nature will contrive a way, either by beta decay, or by neutron or proton emission, or by alpha emission, to get to that lowest mass energy level. And all of that came out of the now corrected semi-empirical mass formula, which, whilst it certainly isn't perfect by any means, but at this level it gives a very good indication of why you have only some stable nuclei, why you have some unstable nuclei, and why some nuclei just don't seem to exist at all. Final point to make is that in general, the greater the mass difference between the start point and the end point, the faster the decay will happen. So if you have a large mass difference, the half-life that is the time for half of it to change, will be very fast indeed.